So we have a real inner product space V, and we say vectors V and W are orthogonal or perpendicular if their inner product is 0. And we say vectors are parallel if one is a scalar multiple of the other for some scalar which is different from 0. And if you have any vector V, we'd like to decompose it into a piece that is parallel to W and a piece that's perpendicular to W. So we would like to be able to decompose the vector V into a sum of two vectors, one parallel to V and the other perpendicular to V. So this is the parallel component and this would be the perpendicular component. So how do we do that? It turns out there's a unique way to do it. There's only one way it can be done. So suppose that this parallel component is C times W for some C. If V is going to be equal to a parallel component plus a perpendicular component, then once you have the parallel component, the perpendicular component can only be V minus this parallel part. Just subtract this from this, which is V minus some scalar times W. So V perp is V minus CW for some W, but V perp, this perpendicular vector, that perpendicular means the inner product with W is 0. So we have the inner product of V perp and W has to be the number 0. V perp is V minus CW, inner product with W. This is VW minus CWW, which is, this is just, well, I can leave it like that. If that equals 0, when you solve for C, we get CWW is VW. W, I should have said, is non-zero. It doesn't make any sense to decompose a vector with respect to 0. So C is equal to the inner product of V and W divided by the inner product of W with itself. So V perp is the inner product of V with W over the inner product of W with itself times W. So this is the formula for the component of a vector V perpendicular to the vector W, or orthogonal to the vector W. And this very simple calculation is the basis of the Gram-Schmidt orthogonalization algorithm. So we say that a set S of vectors is orthogonal if every two vectors in the set are perpendicular or orthogonal to each other. If the inner product of V and W is 0 for all vectors V and W in S. Sometimes we like vectors whose length is 1. It just makes things a little bit simpler to calculate. So we say that a unit vector is a vector U such that the length of U is 1. And if W is any non-zero vector, if you let U be equal to 1 over the length of W times W, then the length of the vector U is the length of the vector 1 over the length of W times W. You remember the length of a vector is the square root of the inner product of the vector with itself. This is the definition of length. And we know that the length of a scalar times the vector is the absolute value of the scalar times the length of the vector. So here we have a scalar. I can take it outside. This is 1 over the length of W times the length of W. These cancel. This is 1. So if I take any vector W and divide by its length, I get a unit vector. U is called, it's not just parallel to W, this is called the unit vector in the direction of W. And we say a set S of vectors is orthonormal if first S is orthogonal, so every pair of vectors in S is perpendicular, and every vector in S is a unit vector. Now, so recall in Rn, the standard inner product is defined as follows. If V is the vector x1 down to xn, those are the coordinates, and W is the vector y1 to yn, those are the coordinates, then the inner product of V and W is the sum of the pairs of the coordinates. Right? This is exactly the dot product you learned in Calc 3 in 2 dimensions and 3 dimensions. Now, you also recall that let V be a vector space of dimension n, and let V, say V1 up to Vn, be a basis for the vector space. So if V is any vector in the vector space, then V is some unique linear combination of the vectors in the basis, and what is called the coordinate vector of V with respect to this basis it's just x1 down to xn. So this is a vector in Rn, but V is not a vector in Rn. This is just the coordinates of V written as a vector in Rn. Now, suppose B is an orthonormal basis for the vector space. So remember what that means. It means every two different vectors are perpendicular to each other. So if I is different from j, then the inner product of vi and vj is 0. And if I equals j, then the inner product of vi and vj is the inner product of vi with itself. That's the length of vi squared. But if this is an orthonormal basis, that means every vector is a unit vector, every vector in the basis. So the length is 1. So the inner product of vi and with itself is 1. So in other words, the inner product of vi vj is this function we call the Kronecker delta. That is delta ij is 1 if I equals j and 0 if I is not equal to j. And in the case of a vector space with an orthonormal basis, the inner product reduces to the standard inner product in Rn, the sum of the coordinates. And the calculation is very simple. So suppose V is summation xi vi. I goes 1 up to n. So, and W is summation yi vi. I goes from 1 up to n. So the coordinate vector of V with respect to B is x1 to xn in Rn. And the coordinate vector of W with respect to B is y1 to yn in Rn. Let me use the letter J here just to make it easier. So what is the inner product of V and W? That's summation xi vi inner product with summation yj vj. I goes from 1 to n. J goes from 1 to n. And when you expand this by the bilinearity, this is summation I goes from 1 to n. Summation j goes from 1 to n. xi yj inner product of vi vj. This is summation I goes from 1 to n, summation j goes from 1 to n, xi yj delta ij. Of course, this inner product of vi and vj is the Kronecker delta. And this is 0 except when j equals I. So this is just the sum I goes from 1 up to n, xi yi. All the terms that j different from I disappear. And this is exactly the standard inner product of the coordinate vectors in Rn. So this is the standard inner product in Rn. So if you have an orthonormal basis for a vector space, it makes it very easy to calculate the inner product. And it's a natural question then, if you have any basis for your vector space, is there a way to transform it into an orthonormal basis? And the answer is, of course, yes. And that process is called the Gram-Schmidt orthogonalization process. So let me repeat the lemma that was in the previous lecture. It says the following. So we have a vector space V, a subspace W of V, And suppose that W1 up to WK is an orthogonal basis for W. So here's a sort of a picture. Here's W, here's V. Suppose that, so your subspace W, which is not equal to V, it's properly contained in V. So there's some vector, I'll call it W prime, that is outside of W, any vector that's outside of W. So let W prime be in V, but not in W. So we know the set W1 up to WK together with W prime is certainly linearly independent. That was actually a question on the last exam. If you have a basis for a subspace W and you take any vector that's not in the subspace and add it to the basis, you get a larger linearly independent set. And suppose we let W prime be the subspace spanned by W1 up to WK and W prime. So this is not necessarily all of V, but it certainly is a larger subspace that contains W and this vector W prime. Right. There exists a vector W sub k plus 1 such that the set of k plus 1 vectors, W1 up to WK, plus this new vector is orthogonal and spans W prime. So I can find a vector to add to W, so I have an orthogonal basis for this new larger subspace W prime. And the proof is the following. We have WK plus 1 equal to, so I want W prime to be perpendicular to each of these K vectors. So I subtract the component of W prime perpendicular to each of these vectors. So for each I, from 1 to K, the component of W prime perpendicular to Wi is the inner product of W prime Wi divided by the inner product of Wi with itself times Wi. So that's kind of a formula. In any case, this WK plus 1 is a linear combination of W1 up to WK and W prime. So this is certainly in my new vector space. And I claim that this is perpendicular to all the other vectors W1 up to WK. So suppose I take the inner product of WK plus 1 and Wj for any j from 1 up to k. So WK plus 1, that's this vector. W prime minus summation. Well, maybe I'll put this on and give myself some more space. Let's see. So I have WK plus 1 is the vector W prime minus the component of W prime and the component of W prime parallel to each of the other vectors in the basis. So that's the inner product of W prime Wi over Wi Wi. So this is a scalar times the vector Wi. And for every j from 1 up to k, I want to show that the inner product of wk plus 1 and wj is 0. So this is wk plus 1. So I have in here w prime minus the sum from 1 to k, w prime wi over wi wi, inner product with wj. And then I expand this by bilinearity. This is w prime wj minus the sum, I goes from 1 up to k, w prime wi over wi, that's just a scalar, times the inner product of wi with wj. So I have this inner product minus this sum of scalars times an inner product. But the inner product of wi and wj, that's delta ij, that's the Kronecker delta. This is 0 unless I equals j. So the only term which is not 0 is the term when I equals j. So I have w prime wj minus, and I only have to look at the case I equals j. When I is equal to j, this is w prime wi over I equals j, wj, wj, inner product wj. These cancel. This is the inner product of w prime wj minus the inner product of w prime wj. That's 0. So wk plus 1 is perpendicular to all of the wj's. So the set w1 up to wk plus 1 is orthogonal. Every pair of vectors is perpendicular. And w prime is a linear combination of w1 up to wk plus 1. So this set is orthogonal and spans w prime. That's what I wanted to prove. And this teaches us how to construct an orthogonal basis for a vector space once we have a basis for the vector space. So let me maybe pick an example from the notes. Yeah. So in R3, let B be a basis for R3 consisting of the following three vectors. So V1 is 0, 1, 1. V2 is 1, 0, 1. And V3 is 1, 1, 0. So this is a basis. But what is the inner product of V1 and V2? Well, 0 plus 1, 0 times 1, 1 times is 1. It's not 0. V1 and V2 are not perpendicular. What's the inner product of V1 and V3? It's also 1. It's not 0. What is the inner product of V2 and V3? It's 1. It's not 0. So no pair of these vectors is perpendicular. But I want to obtain from this basis an orthogonal basis. So I can start with W1 and let it just be equal to V1. So that's going to be the vector 0, 1, 1. And now I want to get from V2 another vector that's perpendicular to V1. So I want to let W2, right? So what do? I take V2 and I subtract I want V2 perpendicular to W1. So, oh, sorry, I want W2 perpendicular to W1. So from V2, I subtract V2 minus inner product W1 over W1 inner product W1 times W1. Let's see what that is. V2 is the vector 1, 0, 1. The inner product of V2 and W1 is the same as the inner product of V2 and V1. It's 1. The inner product of W1 with itself is 2 times W1, 0, 1, 1. So that's 1, 0, 1 minus the vector 0, a half, a half. That's the vector 1 minus a half and a half. What is the inner product of W1 and W2? It's the inner product of 0, 1, 1 and 1 minus a half, a half. You get 0 minus a half plus a half is 0. So W1 and W2 are perpendicular. That's pretty good. So I have my W1 is V1. My W2 I just calculated from V2. Let me get my W3. So W3 is going to be V3 minus V3 W1, W1, W1 times W1 minus V3 W2, 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 W2. So that's a little calculation that I have to do. So this is all now just simple vector arithmetic. V3 is the vector 1, 1, 0. The inner product of V3 and W1 is 1 over the length of W1 squared. The inner product of V1 with itself is 2 times the vector W1 minus the inner product of V3 and W2. So this is W2, 1, 1, 0, 1, 1, 0 is 1 minus a half. That inner product is a half over the square of the length of W2. That's 1 plus a fourth, that's 3/2, times the vector W2. So this is 1, 1, 0 minus the vector 0, a half. This is a half over 3/2 is a third. So this is minus a third times this vector. That's a third minus a sixth plus a sixth. So when I calculate this, what do I get? 1 minus a third is 2/3. 1 minus a half is a half. A half plus a sixth is 2/3. 0 minus a half minus a sixth is minus 2/3. So I started in R3 with the basis v equal to the vectors 0, 1, 1, 1, 0, 1, and 1, 1, 0. And I constructed a new basis with the vector 0, 1, 1. Let's see, because W1 was V1. The second vector I constructed was 1 minus a half. And the third vector I constructed is 2/3, 2/3, minus 2/3. And we check that the inner product of these two is 0. You can compute the inner product of these two is 0. And the inner product of these two is 2/3 minus a third is 0. So this is an orthogonal set of vectors. Every two of these vectors is linearly independent. And every orthogonal set is linearly independent. R3 has dimension 3, so this is a basis. So this is an orthogonal basis. Suppose I want an orthonormal basis. Just replace each vector by a unit vector in the same direction. So that means I divide each vector by its length. So if I have the vector W1, which is 0, 1, 1, the length of W1 is the square root of the sum of the squares of the coordinates, the square root of 2. W2, 1 minus a half. The length of W2 is the square root of 1 plus a fourth, which is the square root of 3/2. And the length of W3 is 2/3, 2/3 minus 2/3. So the length of W3 is the square root of, each of these squared is 4/9. 4/9 plus 4/9 plus 4/9. That's 3 times 4/9. So we get 2/3 times the square root of 3. So if I take the unit vector U1, which is W1 divided by the length of W1, the length of W1 is 1 over the square root of 2. W1 is 0, 1, 1. So I get the vector 0, 1 over the square root of 2, 1 over the square root of 2. The vector u2 is the vector w2 divided by its length. The length of w2 was 1 over, is the square root of 3 over 2, so 1 over that is the square root of 2/3 times the vector w2, 1 minus a half. So if I can do my arithmetic correctly, this looks like, but I'm not sure it's right. So 1, a fourth, and a fourth. Yeah. Square root of 2 over 3. I'm not sure. Square root of 2/3 minus a half times this is minus 1 over root 6. And a half times this is plus 1 over root 6. I could write this as 2 over root 6. So it all looks similar. And u3 is the vector w3 divided by the length of w3. The length of w3 was 2 root 3 over 3. So this is 3 over 2 root 3 times the vector w3, which is 2/3, 2/3 minus 2/3. So this is equal to the vector, this times 2/3 is 1 over root 3. This times 2/3 is 1 over root 3 and minus 1 over root 3. So you can check each of these vectors, u1, u2, and u3, has length 1. These are all unit vectors. These vectors are mutually orthogonal. The inner product of any two of these vectors is 0. Yeah. So this is my orthonormal basis. So this is an orthonormal basis. So this algorithm, called the Gram-Schmidt orthogonalization or orthonormalization process, starting with any finite dimensional vector space and any basis for the vector space, constructs an orthonormal basis. And that's not necessarily the object of life, but it is certainly one of the objects of linear algebra to be able to do this. So this is quite interesting. While we're dealing with the inner product, there's the following very important notion. We know what it means for two vectors to be perpendicular. So vectors v and w are perpendicular or orthogonal if the inner product is 0. And I want to extend this to the idea of having two subspaces that are perpendicular. So we have this vector space V, and sitting inside V, we might have two subspaces, W1 and W2. So we say that subspaces W1 and W2 are orthogonal. if for all vectors W1 in the subspace W1 and little w2 in the subspace big W2, their inner product is 0. Let's take two simple examples of orthogonal subspaces. Suppose we're in R2 and we let W1 be the x-axis. That's a subspace. This is all vectors of the form x0. And we let W2 be the y-axis. That's all vectors 0, y. And what happens if you take the inner product of x0 with the inner product of 0, y? That's x times 0 plus 0 times y is 0. All that's saying is any vector on the x-axis is perpendicular to any vector on the y-axis. So these are orthogonal subspaces. Or for example, in R3, you could take W1 to be the xy plane and W2 to be the z-axis. And then any vector in the xy plane is perpendicular to any vector in the z-axis. These are like simple examples of orthogonal subspaces. So the basic sort of geometrical fact that underlies this idea is the following. So we have X, a subset, not necessarily a subspace, just a subset of my vector space V. Let X with this perpendicular sign above it. We read this as X perp for perpendicular. So let X perp be all the vectors V in V with the property that V is perpendicular to X. The inner product of V with X is 0 for all X in the set X. And the lemma says, no matter what X is, X perp is a subspace of V. So if you take any collection of vectors in V and you look at everything that's perpendicular to them, that forms a subspace. And the proof is simple enough. Suppose we let V1, first of all, 0 is an X perp because the inner product of the 0 vector with X, with any vector, is 0. So the first condition of a subspace is that it contains the 0 vector, and X perp does. And if V1 and V2 are in X perp, and C is any scalar, then the inner product of CV1 plus V2 with X, if you just expand this by the bilinearity, it should be a comma. This is CV1X plus V2X. But V1 and V2 are perpendicular to X. This is C times 0 plus 0 is 0. So C1 plus V2, C1 V1 plus V2 is an X perp. For any vectors V1 and V2 in X and any scalar C, so X perp is a subspace. And this gives us the following very beautiful result. It says the following. I'm not sure why I called this a lemma. It should be a theorem. it says you have a vector space V with an inner product, a real vector space, and the dimension is n, and W is a subspace of V with the dimension of W equal to K. Then W perp is a subspace of complementary dimension, a subspace of dimension n minus K. So here we have V. I have a subspace W. This has dimension K. There's always going to be the space W perp of everything perpendicular to W. It's going to have dimension n minus K in the subspace of dimension n. Proof. Well, suppose we let W1 up to WK be a, well, let's make it easy, be an orthogonal basis for W. Every vector space has a basis. By Gram-Schmidt, there exist vectors WK plus 1 up to W sub n such that the set of n vectors is a basis for V and an orthogonal basis for V. Okay. Using the Gram-Schmidt process, we can extend any orthogonal basis for a subspace to an orthogonal basis for the whole space. Supposedly we let V be any vector in the vector space. So you can write V as some linear combination. I goes from 1 up to n of the vectors in this orthogonal, this is Wi, in the vectors in this orthogonal space. Now, V is in W perp if and only if the inner product of V and W is 0 for all W in the subspace W. And it's enough that V and Wi is equal to 0 for all I from 1 up to K, because W1 up to WK is a basis for the subspace. I'll write this Vj. But what is V inner product with Wj? That's summation xi, Wi, Wj. But this is an orthogonal basis. Wi, Wj is 0 unless I is equal to j. In fact, let's make it orthonormal. So every vector has length 1. This is just equal to x sub j. So the inner product of V and Wj, which is xj, has to be 0. So V is the sum xiwi, I goes from j plus 1, sorry, k plus 1 up to n. So this perpendicular subspace, this orthogonal complement to W, is all vectors which are linear combinations of these n minus k vectors. So this subspace is generated by this set of n minus k, the independent vectors that has dimension n minus k. So again, this is sort of written down carefully in the notes, and it's a very interesting idea, this orthogonal complement. And in fact, it also says that every vector in V can be written as a vector in W plus a vector perpendicular to W. You always have that kind of decomposition of a vector, which is a geometrically interesting fact. Okay, well, that's all I'm going to do this morning. If there are any questions, good. If not,